Before we continue looking at whether a sequence converges or diverges, let's review factorials. Now, a factorial, like this, n factorial, that exclamation point is red factorial, is defined as n factorial is 1 times 2 times 3 times 4 times dot 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 times n minus 2 times n minus 1 times n, or the way we mainly think about it is just written the opposite way. It's going to be the product of n all the way down to 1 by subtracting off one integer for each one of these. So n times n minus 1 times n minus 2 times n minus 3 times dot 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 all the way down to 1. We also define factorials as 0 factorial is equal to 1 and 1 factorial is equal to 1. So let's simplify the ratio of factorials in examples 6 and 7 and then determine if a sequence that uses factorials converges or diverges. One of the ways to simplify the ratio of factorials is to list out all of the numbers you're multiplying. So 6 factorial is going to be 6 times, 5 times, 4 times, 3 times, 2 times 1, because it's going to be that n all the way down to 1, subtracting 1 each time. 10 factorial would be 10 times, 9 times, 8 times, 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1. Well, notice that this has 6 times 5 times 4 times 3 times 2 times 1, and so does the denominator, so we know that that's going to cancel, and we're really looking at 1 over whatever 10 times 9 times 8 times 7 is. So if we're trying to figure out what is 10 times 9 times 8 times 7 on a calculator, we end up with 5040. So this is equal to 1 over 5040. There's a shorter way to handle simplifying the ratio of factorials. If you have 6 factorial over 10 factorial and you're trying to simplify it, you look at your two factorials and you determine of these two which one is smaller. The smaller one is 6 factorial. That means that that's the one that you are not going to expand, and you'll then expand the larger factorial, in this case 10 factorial, until you get to 6 factorial. So this will be 10 times 9 times 8 times 7 times 6 factorial. And then you're able to cancel those terms a lot quicker, and you get the exact same thing that you did here. This is still equal to 1 over 5040 because all you're left with in that denominator was that 10 times 9 times 8 times 7. Let's simplify number 7. The first thing you ask yourself is, which one of these is bigger? Is it 2n plus 1 factorial or is it 2n factorial? Well, 2n plus 1 factorial here is bigger, therefore this is going to equal, if I expand 2n plus 1 factorial, it's just going to be 2n plus 1 times 1 less, would be 2n plus 1 minus 1, or 2n factorial. I don't expand the denominator because that guy was a smaller one. And then I notice that my 2n factorials cancel. Therefore, this is just equal to 2n plus 1. Let's do number 8, where we're determining if this sequence converges or diverges. If it converges, we're finding its limit. Well, how do I do that? I have to take the limit as n goes to infinity of this n plus 3 factorial all over n factorial. Well, I don't really know how to handle this with factorials, so what we want to do is we actually want to simplify this ratio first and then try to find the limit. You look at these two again, n plus 3 factorial and n factorial. Which one of those is bigger? N plus 3 factorial, that's the one you expand. So we say here the limit as n goes to infinity of, if I expand n plus 3 factorial, I end up with n plus 3, minus 1 is n plus 2, minus 1 is n plus 1, minus 1 is just going to be n, and then I write n factorial. The denominator stays as n factorial. We don't expand it because it's the smaller one. Then my n factorials cancel, and all I'm left with is the limit as n goes to infinity of n plus 3 times n plus 2 times n plus 1. Well, what's the limit as n goes to infinity of that? Well, this would just be infinity times infinity times infinity. And this, remember, that's not an indeterminate form. Infinity times infinity is just equal to infinity. since we wrote infinity, we know that that means that this sequence diverges. Let's look at the following two theorems for sequences, and then we're going to continue to determine if a sequence converges or diverges. The first one we want to look at is the squeeze theorem for sequences, and it's very much like the squeeze theorem for functions that you learned in Calculus 1. We say if the limit as n goes to infinity of a sub n is equal to L, and the limit as n goes to infinity of b sub n is equal to L, and there exists some integer n such that once you reach n, a sub n is always less than or equal to c sub n, which is always less than or equal to b sub n, for all n greater than n. So at some point, a sub n is always the smallest, c sub n is always the one in the middle, and b sub n is always the biggest. Then, if that is true, then that means that the limit as n approaches infinity of c sub n must also equal L. Recall in Calculus 1, we had it as functions, so I'm going to show it as functions instead of as sequences. Basically, in Calculus 1, we had three functions. We had f of x, and we had g of x, and we had h of x. And what we said was, if you have f, and f is the smallest, and then you have g, and g is the one in the middle, and then you have h, and h is the biggest one, and that you can show that the smaller one and the bigger one at some c are approaching some number L, then the one in the middle must also be approaching that number L. So we're doing the exact same thing with limits of sequences that we did in Calculus 1, except for instead of looking at it approaching some number c, now we're approaching infinity. One more theorem to look at, and that's the absolute value theorem for sequences. And what that says is that if you have a sequence a sub n, so you have this formula here for a sub n, and you take the limit as n goes to infinity of the absolute value of that formula. So you take the absolute value of whatever this is, and that limit is equal to 0, then without the absolute value, you're equal to 0. Basically, this here is letting you know that if you have a sequence that alternates between positive and negative terms, if you take the absolute value of that sequence and you end up getting the limit as n goes to infinity of that absolute value equal to 0, then the sequence without the absolute value, the original one, will converge, and it converges to 0. Let's look at examples 9 and 10. 9 and 10 have the same directions. Determine the convergence or divergence of the sequence given the nth term, and if it converges, find its limit. Well, I look at number 9 and I notice that this guy here alternates because it's a sub n equals negative 1 to the n times 2n minus 1 all over n squared plus 4. The first thing I'm going to want to do here is find the absolute value of this sequence. So what's the absolute value of negative 1 to the n times 2 to the n minus 1 over n squared plus 4? Well, if I'm taking the absolute value, this piece here that alternates between positive and negative and positive and negative is just going to cancel. This is just equal to 2 to the n minus 1 over n squared plus 4. Now what I need to do is find the limit as n goes to infinity of the absolute value of a sub n, which we know is equal to the limit as n goes to infinity of this guy here, 2n minus 1 over n squared plus 4. Well, currently this is going to be infinity over infinity because it's 2 times infinity minus 1, which is infinity, and then infinity squared plus 4, which is infinity. So what we do is we go to the Calculus 1 way instead of using L'Hopital's rule, because usually this is faster. Put these two terms over each other, reduce, and then take the limit again. Well, what's the limit as n goes to infinity of 2 over n? Well, that's going to be 2 divided by infinity, or 0, because remember, anytime you have a constant over a variable raised to a power, that you are equal to 0. Since we're equal to 0, what this means is that our sequence, a sub n, converges. And the limit of that sequence, again, is equal to 0. What about example 10? In order to figure out if it converges or diverges, we need to find the limit as n goes to infinity of In this case, cosine of n pi over the square root of n. As n goes to infinity, if I'm looking at the cosine of n pi, I know that that guy is going to be oscillating between positive and negative 1. It's going to be negative 1 and then a positive 1 and then a negative 1 and then a positive 1, etc. Right? It's going to be oscillating because that's what cosine does. And so it's going to be all that over the square root of infinity. So does this limit exist? We're not sure. Well, what we could do is we could use the squeeze theorem for this particular sequence. Again, we know that the cosine of n pi is trapped between negative 1 and positive 1. But we don't have the cosine of n pi, we have the cosine of n pi over the square root of n. So we're going to place each one of these terms in this compounded inequality over the square root of n. What this is saying is that negative 1 over the square root of n is that smaller function, 1 over the square root of n is that bigger function, and if I can find the limit as n goes to infinity of the smaller one, the limit as n goes to infinity of the bigger one, then the limit as n goes to infinity of the one in the middle must be whatever those two equal. So let's find out what the limit as n goes to infinity of this smaller function is, negative 1 over the square root of n. And that's a constant over n raised to a power. We know that that's equal to 0. What about the limit as n goes to infinity of 1 over the square root of n? Well, that's the same thing. It's going to be a constant over n raised to a power, that's equal to 0. Therefore, by the squeeze theorem, we know that the limit as n goes to infinity of the cosine of n pi all over the square root of n must also equal 0. And that means that our sequence converges.